All right. Welcome, everyone. Thank you all for coming out today for our RSCA in 5, which is focused on the CHIPS and Science Act. I wanted to welcome both the people in the room and those who are who are on the live stream today. So let me first introduce the RSCA in 5 series. It's our flagship speaker series at SJSU, and it allows our faculty to showcase their research in 5 minutes around a specific theme. My name is Emily Chan, and I'm the Director of Research Engagement. Today, we're going to discuss the CHIPS and Science Act and what SJSU is doing to make strides in this area. The CHIPS and Science Act was signed into law in 2022, earmarking almost $150 billion worth of funding between companies and the government. This funding is aiming to produce and boost semiconductor research and production in the United States. SJSU is poised to meet some of those demands as a centrally located university in the heart of Silicon Valley. And today you're going to hear from our faculty members who will, and as well as our industry research alliances specialists about SJSU's work in this area. So without further ado, I'm going to pass the mic over to our Associate Vice President for Research, Richard McCarskey, for some opening remarks.
Hey, everybody. Can I use this? Okay. How's everybody doing? So I want to welcome everybody. I want to welcome everybody and sort of frame the event a little bit through the prism of Washington, D.C. So as we know, semiconductors are everywhere, and you're going to hear from our faculty today about both the process of creating semiconductors and how we can make that better, but also some of the back-end application uses from biosensing to robotics, right? The application, and we all know they're impacting healthcare, they're impacting AI, they're impacting our cell phones, et cetera. And the CHIPS and Science Act really represents the first significant investment in the semiconductor research and training and production that the U.S. has done in years. And what we're learning is that investment is hard to get out the door, right? Anybody who's noticed the slow trickle of RFAs, we're a couple years out from the signature and multiple years out from this coming into place. We all know that they're struggling to get the money out the door. So I'm going to talk about my last visit to Washington, D.C., where I met with 3 different folks involved in the CHIPS and Science Act in D.C. to hear their own frustrations, not just ours, and how SJSU potentially has an opportunity to elevate the work our faculty are doing to help solve some of the problems that the federal government is having. So the first person I met with was Dr. Greg Yerk from NIST and the National Semiconductor Technical Center group. He's running that technical center. And what he said to us was they know who the companies are. They don't know who the universities are other than the big universities. And they're struggling to get folks at where they need them to be, which is somewhere between application and discovery, right? That sort of valley of death that we all hear about. And they were really interested when we were talking about what we did at San Jose State and the understanding that we're training students on how to be in the labs, how to work in a fabrication facility, but also that we are working with each other across disciplines. That was the thing that he struggled to understand, and that we had access to things like innovation, right? So they struggle to get people excited and to keep people excited about the getting things to market. And he understands that most of the money, and he told us most of the money is going to go to new fabrication facilities, but they can build all the fabrication facilities they want if we're not filling those fabrication facilities with people who can run them, but also people who can bring new ideas to make things better. The next person I talked to was Michael Littman, who's the division director at NSF for Information and Intelligence Systems and has been tasked with running AI, like the AI strategy across NSF. Michael's an interesting guy. He's a full professor at Cornell. This is the third time I've met with Michael, and every time I meet with Michael, I feel like he lets his guard down just a little bit more. The first time I met with him, he basically looked at us like we had two heads. Why would I need to talk to San Jose State? Everybody else is doing this, who's doing this work. I know who they are, and I don't know you folks, right? By the third time, he started to understand. We are the engine that Cornell isn't, frankly, of getting these kinds of techniques into the students' hands to help power the AI revolution. And he also understood our value in being truly collaborative. He mentioned how some of the work they were doing, I mentioned some of the work we were doing on campus, specifically some of Hillary Hurst's work and Isan's work. And he said, oh, that sounds like something we should be funding. I said, well, it's funded by the Department of Energy. And he said, why would the Department of Energy fund that? That's our realm. And so we had a 20, 30-minute conversation about this, and we pulled up the abstracts, and he looked at this, and we saw the turf wars that were happening in real time. And he asked, I need to know these people. I need to reach out to these people. Thankfully for us, our friend Hillary Hurst, if you don't know, is going to OSTP this summer to help with this kind of coordination. And the last person I'll talk about meeting with was Deirdre Mulligan, who is the principal deputy and U.S. Chief Technology Officer for OSTP, the Office of Science and Technology Policy. Deirdre is our neighbor. She's on rotation from Berkeley. She, unlike the other folks I've talked about, actually already understood what SJSU brought to the table. She has had SJSU students in her lab for years, undergraduates and graduates matriculating to PhD programs. And what she talked about was, how do we bring a coordinated effort in the Bay to then be replicated across the country? I talk about all this to say the struggles that we feel, that I know that John in the cluster feels, is how do we get people on our own campus to work together, but also how do we make sure people outside of our campus understand the value we bring to the table, understand the value we bring because we're interdisciplinary, because we're nimble, and because we're not necessarily, we're not the big behemoths. And the federal government is saying every time I go is they don't know how to wrangle all these different people. They don't know how to wrangle people within their own offices. And it sounds great. You go to the NIST office, right? And you expect it to be this lovely, fancy office. It's the new training center, technical center that they just funded. And they're in boxes, and it looks like the building's going to fall apart. It takes 20 minutes to get anybody to help you because there's no support staff. So they are, just like everyone else, trying to staple this together, and they're looking for our support and our help. So what I hope we do today is I hope we learn from our faculty the wonderful things they're doing in the application side, but also in how we better structure semiconductors, how we learn to structure those, and understanding that we are closer together as a group of individuals than a lot of our counterparts, and that's our strength. So I'm really excited for you all to be here, both online and in person. And with that, I'm going to turn it back over to Emily.
Thank you, Richard. Okay, so I have a couple of housekeeping items to go over. As a reminder, we're recording today's events. And we're simultaneously streaming this on Vimeo right now, where we have a fairly large audience of almost 20. There will be some shared Q&A that will happen after all of the speakers have presented. Please raise your hand for questions. Unfortunately, we can't accommodate questions from the live stream audience. If any folks need to leave during in person during the presentations, please do so after applause. And of course, please join us for lunch after the presentations and shared Q&A. So here is our agenda for today. And there's a QR code on that slide. I encourage you to take a look at that. That provides a link to our speakers' biographies. And I'll show this again at the end of the presentation today. And without further ado, Let me introduce our first speaker, Dr. Jason Kim, who is our Industry Research Alliances Specialist in the Office of Innovation, where he is going to speak about NextFlex and SJSU. Please welcome Jason. Thank you.
Thank you, Emily. Hello, my name is Jason Kim, and I am the Industry Research Alliances Specialist in the Office of Innovation. Thank you all for joining us today. Today, I wanted to talk a little bit about NextFlex, but before, my role here at San Jose State is to help support the Industry Research Partnership portfolio and help in partnership development with industry collaborators. And I also wanted to talk about how those approaches are being addressed with NextFlex, which is a consortium of government, nonprofit, companies, and academic institutions that are all coming together under one umbrella with a shared goal of building manufacturing and innovation in flexible hybrid electronics in the US. And so the challenges that Richard spoke to earlier of bringing all these people and different parties together, NextFlex has successfully done these things. And I wanted to talk a little bit about our involvement. So San Jose State has recently joined and received an institutional membership. And so I wanted to talk about the benefits to participate, which is open to all San Jose affiliates, and how we can build partnerships together across industry, academia, and government. And so NextFlex is aptly dubbed America's Hybrid Electronics Manufacturing Innovation Institute. And so they have three-pronged mission, one being growing US competitiveness with hybrid electronics technology, which I'll also go into more in a little bit. Two, build a sustainable ecosystem to support manufacturing of the technology. And three, accelerate the growth of the next generation of workforce for advanced manufacturing in the US. Now, hybrid electronics, specifically hybrid flexible electronics, refers to a new class of electronics that combine printed and additive manufacturing with performance of semiconductor devices, as you can see here. And these have a whole range of applications due to their flexible, conformable, stretchable features. They're lightweight, low cost, and fast to market, and are more environmentally friendly than those produced from traditional manufacturing methods. You may have seen them used in such cases of the flexible LED displays, phones, smartphones, but the applications for this are numerous in terms of medical devices, biosensors for vehicles, as well as for defense purposes. And so just to give a quick overview of the main areas that NextFlex accomplishes their main goals through, one being the NextFlex Technology Hub, which provides design and prototyping services. Two, the consortium that I spoke to earlier has a total member of 188 memberships, and this includes company partners such as Lockheed Martin, Boeing, Jabil, Siemens. And they have regular communication to bring this group together through webinars, workshops, and technical project group calls, newsletters, as well as their award-winning nationwide workforce development programs. And this tries to address the talent pipeline development starting at K through 12. And importantly, the project calls that we can join have had 136 million devoted to developing this flexible hybrid electronic manufacturing. And if you join these 11 technical working groups that are part of NextFlex, then you can join the project calls to learn more about their 5-year roadmaps and the validation of market needs that are coming from industry experts that are part of the member consortium. Now, I won't go into all the different technical working group areas, but there are two main focuses with manufacturing thrust areas and technology platform demonstrators. Each team is led by over 150 subject matter experts and co-leads, and they collaboratively determine the project call's direction and focus on funding. Now, before I leave, I wanted to give a call to action for you today. If you could please all join us for a technical call with NextFlex, which will be held later this month, where we want to get more faculty members engaged to learn more about the opportunities at NextFlex. You can please create a free user account. Anyone with an SJSU email can join and explore member portal, which has past webinars. You can sign up for the newsletters to join in on the project calls with the technical working groups. And please also join us for a site visit, which NextFlex was very kind enough to invite us to. Their facilities are located in San Jose, about 10 miles north from us, and we will have the dates for you all soon. And all of this information I have in an onboarding document, so please contact me for more information. And thank you to everybody who has been a part of this, from College of Engineering to RNI, and of course the faculty members and our supporters at NextFlex. Thank you.
Thank you, Jason. That sounds really great. We'll learn more about maybe some opportunities to get involved during the Q&A session. But now I'd like to welcome Dr. Yoon Wang from the Biomedical Engineering Department here at San Jose State as she discusses her topic, biosensors for healthcare and food safety. Please welcome Dr. Wang.
Thank you, Emily. Hello, everyone. My name is Yoon Wang. I'm assistant professor at biomedical engineering. Today, I'm going to talk about my research of biosensors for healthcare and food safety. So I would like every one of you thinking about the needs in these different cases. For example, the pandemic we just experienced, and in the cases for food illnesses and outbreaks, and also if someone wants to go to hospital to get a disease diagnosed. So the needs there, we need rapid, accurate, easy to use, and low cost diagnostic or detection methods. But now the issue with the major methods we're using there is usually you will go for many different tests to get diagnosed, confirmed, right? And some of the tests are really slow, and some of them are not telling you the true information. Sorry, and some of them cost a lot, and in some cases there's not enough equipment or trained personnel to run the test. So my research is address these needs and to solve these problems. My solution are using biosensors. So biosensors ensures they are analytical devices based on the interactions between biomolecules, between your target analyte and the sensing element. And this interaction is transduced to signals that can be detected and viewed by the operators. So they have the advantages, very high sensitivity, means very accurate detection, and very short detection time. They can be used for different functions, and they can be very small to become wearables, implantables, and they cost only much less than the other tests, and very simple for users to use them. So my research is combining this biosensor to different new technologies like nanotechnologies, microfluidics, microelectromechanic systems, AIs, and more. So I'm going to give you two examples of research I'm currently working on to see how these biosensors work, those developing in our lab. So first type of biosensor we are majorly focusing on are multiplex biosensors, means they are those one-stop detection methods for multiple different analytes. So here is an example detection of this very harmful and potent toxin, which is botulinum neurotoxin. So we develop a microfluidic biosensor. They can detect this toxin when they are in active form. So we can detect multiple serotypes using the sensor. As you can see here, we have a quantum dot. So that is our signal source. So we have this specific peptide detect a specific serotype of this toxin. When the toxin is there, they cleave in the middle of the peptide. You can see on the bottom left, right? So you can cleave that quantum dot away. So in these two cases, you can differentiate by the signals provided by the quantum dot whether there is a toxin or not. So in this case, we can design different peptide and quantum dot to match different serotypes. So as you can see on the other side, there are A, B, E different serotypes detected. So we can differentiate different serotypes just in one stop just one sample. The bottom picture showing you our current detections for type A and type F. So we can detect as low as 0.1 nanogram for A and 1 nanogram for F, which is relevant to those quantity harmful for people. The other type of solution we have is self-powered biosensor. So this type of sensor we develop in our lab uses a specific modified chip, very tiny, 5 by 4 millimeter. So they serve as both battery and sensor. So you do not need external power to power the sensor and to give you the contamination level. So different from the COVID strip, it doesn't tell you how much virus is there. This sensor can tell you that. And this is based on the special designed sensor we have. They have blocking layer. Once there is the toxin or any other target, for example, the pathogen here we're targeting on, they remove that blocking and give you current signal, as you can see on the bottom right figure. So you can see the current difference to tell you the contamination level. And also, we generate a power, which is about 0.842 with that small area chip, and that gives you the power to power any displays, for example. So my research, moving forward, we will hope to combine the healthcare data to generate a one-stop integrated diagnostic monitoring system platform. Thank you so much. And also, I want to acknowledge my lovely students. Thank you.
Thank you so much, Dr. Wang. I'd now like to welcome to the podium Dr. Christopher Smallwood from the Department of Physics and Astronomy as he talks about optical characterization of semiconductor nanostructures.
All right, thanks so much, Emily. I will, so my research is in the area of optical characterization of semiconductor nanostructures. It's really exciting to actually be here and to sort of like learn about all the things that different parts of the university are doing and sort of what we're looking at even beyond that. I wanted to start off with my own research. So I'm in the Department of Physics and Astronomy. We think a lot about sort of deep, fundamental questions in physics and astronomy. My own research is in the area of looking at spectroscopic investigations of those things. It's very informed by quantum mechanics, oftentimes oriented toward quantum information science. And so I wanted to sort of kind of open things up a little bit by posing a question. There's quantum information science on the one hand. On the other hand, we have sort of semiconductors is very almost garden variety. We're in Silicon Valley, right? And so it's maybe worth asking the question, do quantum information technology and semiconductors belong together? These are two really big, maybe intense ideas. And sometimes those go together well, sometimes they don't. What happens when you take Olaf and put him into the hot tub? Do you get something like maybe chocolate and salt? You get this really awesome mixture. Or do you get milk and orange juice, which is something you might have tried when you were 5 and probably never want to do again? I want to make an argument that this is a really important and fruitful sort of area to look at the sort of intersection between. There's a lot of history for that. Yoon actually talked about it already with looking at biosensors. Quantum dots, which you see over here in the upper right, is a sort of a place where you take semiconductors, you bring them down to nanoscopic dimensions. Quantum mechanics starts to play a role. You can actually change the color at which these sensors emit or absorb. It was the subject of the 2023 Nobel Prize in Chemistry, actually. That's not the only thing you can do. You can also have quantum confinement in just one dimension. And so that leads to quantum wells. That was another Nobel Prize, that one in physics in 2014 for blue LEDs. A lot of the advantages that you have for LEDs are largely facilitated by the fact that you can take layers of semiconductors, bring them down to nanoscopic dimensions. Quantum mechanics starts to give you more control and more power in that area. In my own research, I'm interested in taking that even further. And so I'm interested in looking at point defects. So individual atoms in sometimes semiconductors. I'll actually be talking a little bit about diamond in this case. And those can change the properties of the emission and absorption of light in interesting ways. Also 2D materials. I won't have time to talk about that, but that's another area in which we're sort of exploring right now. So in my lab, it's very, very hands-on and experimental research group. We do a lot of playing around with light, a lot of student involvement, a lot of exploration of lasers, and a little bit in certain areas actually of the technique of interferometry, where you split up your beam sometimes into pulses, sometimes into different beams, and you set up time delays between your pulses. You can vary those time delays. And you can learn things. I guess in some sense, my research is oriented toward learning things about the materials themselves, which can then be applied toward all sorts of different kinds of applications. We do the spectroscopy aspect of that to sort of characterize these materials. This is one example of one of the lasers that we're using in the lab. It's a helium-cadmium gas laser. And we're also interested in looking at temperatures, cycling temperatures up and down, and sort of characterizing how do materials respond in that area. And so then it's only a 5-minute talk, so I only have time to sort of give a very, very small teaser for one very small slice. We have been looking in the past, and this is work that we're continuing to look at theoretically here at San Jose State University. Part of it was also work that I had done as a postdoc at the University of Michigan, where we had used this interferometric technique, a variation of it called multidimensional coherent spectroscopy, to investigate the properties of a defect in diamond called the silicon vacancy center in diamond. The chemical structure looks something like this. What we found when we did that is by sort of poking and prodding at these materials in different kinds of ways, you can often learn new things about existing materials. Sometimes you can even discover new kinds of defects. And the discovery that we made in this case was we took 2 different detection techniques, photoluminescence and heterodyne detection. And by comparing the 2, we were able to discover that there was actually a version of these silicon vacancy centers which are not normally visible in a high density sample through photoluminescence. It only shows up through absorption or through heterodyne detection. You can sort of see that in this picture. I don't have time to go into the details by the very different, but you can sort of see that the pictures are very, very different from each other. And so all of this stripe that you see in the upper left and the lower right, and the picture in the lower right down there, are centers that do not exist in other contexts. And so we want to do more of that. We want to try to explore more materials, more kinds of defects in diamond, maybe defects in these atomically thin semiconductors. And we think there's a lot left to do here, simply by the fact that there's so many different kinds of combinations. Okay, so with that, I'm already a little bit over time. I'll leave you with my acknowledgments and thank you. This is my research group. We're funded by the National Science Foundation, and we benefit from collaboration with a lot of collaborators, both across the nation and across the world. Thanks.
Thank you, Chris. All right. Now we have Dr. Armin Mogadam, who will present on semiconductor wafer alignment detection. He's from the Department of Aviation and Technology. Please welcome him to the podium.
Okay, hello everyone. Good, still morning. So I'm from Department of Aviation and Technology, and on the technology side, we have the specialization of manufacturing, and my research focus is on application of computer vision and deep learning in manufacturing processes. And one of the projects that I work on with my students, of course, is alignment detection in semiconductor manufacturing processes. I'm going to use a little bit deep learning and computer vision to see how we can check the quality of this production during the manufacturing processes. So a little bit background, we have, when you are in the manufacturing production line, when you want to produce a semiconductor, what we do, we usually just lay many layers over each other. And when you do that, you may just generate some errors because those layers can be deviated from the place that we expect them to be. And to monitor that process, that how precise we are to do that, we have some alignments here, as you can see on the left image. So we monitor the X alignment and the Y alignment to see how precisely we put those layers over each other. And how can we monitor this, the precision? We have, as you can see here, we have like a square right here is the center of the alignments, and we want everything like those alignments to be perfectly over each other at the center. If they are not aligned at the center, means we have some errors. And what is that error? Like we are going to look for the perfect alignment, and that perfect alignment, as soon as we find it, we count how many alignment we are off from the center, and we calculate the error. And each alignment is going to generate 0.5 micro meters for us. Okay, how to do that? Right now, we do it like by just looking at the images of these alignments. Like we need human operator in the loop, go over each picture one by one and find those alignments. We wanted to make this automated, so that's we came up with the idea that how about we use some computer vision and deep learning. And this is our basically our lab. This is the wafer that we are working on, and we have the microscope to take pictures of all those alignments that we have. We have like many of them on one wafer. And then we label those images. It means that we are going to label each alignment that this alignment is perfect, this is not perfect, this is perfect. Because ultimately, when you want to train a deep learning model, your model is going to learn from the information that you provide to it. So how do we label that? We use some softwares for labeling. And as soon as you label them, you generate that file that you see there. And that file basically specify the position of each alignment and with the label that this is perfect, this is not perfect. During the training process, deep learning model will go to that position, extract some features from that part of the image that we have, and ultimately learn from it that later you can apply to the new images, and it's going to find those specific alignments for you. Okay, this is why we call it deep learning. You see two examples here, RetinaNet and YOLO version 9, which is very new. And all those layers that you see, those are the layers that we use to train the model. They are going to learn from the images. You see some images here. And usually when you have an application and you want to train a model, you start with the baseline model, you train something, and then you train other models and compare it to the baseline. And we started with RetinaNet, we trained many models, and we ended up on YOLO V9, which is performing acceptable at this point. Okay, and because I have 1 minute, I just go to the results that we have. As you can see here, each alignment, these are the real pictures, and those numbers that you see there, those are the real detections. And the numbers that you see that we have N and P, so it means that not aligned, and P means aligned. And we have some numbers associated with them showing how sure we are. For example, we are 87% sure that that alignment is not perfect, and so on and so forth. So as soon as you find the perfect alignment, you just need to count how far you are from the center and basically calculate the error. And I have some precisions and recall of the model, but I'm out of time, so you can talk to me after this is done. Thank you very much.
Thank you so much. One of the comments that I do want to make is I hope you are collecting your thoughts on people's presentations because we'll have time for shared Q&A. So save those questions for the panel. All right. Wait a moment. We are missing some slides. Let me see, just one moment, please. We'll take a pause. Okay. All right. Thank you for the quick pause. I'd like to welcome Dr. Baheen Elahi from the Industrial and Systems Engineering Department at San Jose State as she discusses robots and vision for semiconductors.
Thank you so much, Emily. Then hello. Today I would like to actually present some portion about my research and also the importance of the robot and vision for the semiconductor and also semiconductor for the robotics and sensors as well. I'm Baheen Elahi, Associate Professor in Industrial and Systems Engineering. And actually, my research area is related to the Industry 4.0, the simulation, robotics, and also the statistical analysis in terms of the design of experiment or quality control, and also optimization. And technically, because my background is in industrial and systems engineering, then from the system-wise, if we want to take care of optimization or even the different scenario planning using the mathematical modeling or operation research. And then, as you know, we have like moving forward from Industry 4.0 to Industry 5.0. And the idea is that in Industry 5.0, then we are also focusing on a sustainable, human-centric solution. And then, as you know, the semiconductor industry, actually, we can see the robust growth in that. And we have actually, because of the demand that we have for the semiconductor in automotive industries, related to, all of those EVs that, will be in the market, and also the data centers, the high performance computing, co-packaged optics, chiplets, high bandwidth actually memory. And also as the quantum computing and quantum computer are moving forward, then technically the advances in semiconductor will be helpful for them as well. And as you can see here, actually this diagram shows us that, for example, in 2032, how much the global market for the semiconductor are increasing. But still, we have the challenges, and also in US and some other countries as well, that we have the challenge of the persistent talent shortage, and also we need the highly specialized workforce. But sometimes even the training or the process in order to come up with like an expert in this area are also very lengthy. And that was, I was thinking of, probably recently, if you have heard about the support for the digital twin, probably using the digital twin because digital twin was belonging to Industry 4.0, but probably these days they are promoting that to probably using for the training of the workforce in this area. And in my lab, we focusing on the robot collaboration and also simulation of the robot in order to come up with analyzing and decision making of the different scenarios. And we are using the different software. For example, this job is through the Simio software that we have, that we can at the same time doing a quantitative analysis, the simulation part, and also analyzing the different scenario and having like a 3D. And also through the robot operating system and Gazebo, which are actually open source, then we have the chance to analyze the different scenarios. And related to the semiconductor, I think that semiconductor for the robotics, actually, the application of the robot in semiconductor, it can be for the mechanical task and also intelligent task. For example, if we have like a sensor-enabled robot that can take care of the image processing and also defect categorization, then if there is a defect, then at a lifetime clarifying that what type of defects and classifying that. And also these days I'm focusing on some research project with my students in order to using the drones for taking like a live images from the different angle, and then trying to actually using through the cloud-based, we will be able to take care of the image processing and having like a quality guardian system to actually avoid the defective part. And then I wanted to also highlight that, since actually my area is related to the robot collaboration and even human-robot collaboration, then probably, there will be more chances for automating the process and using the robot for different phases like the packaging or better vision system for the semiconductor. And semiconductor also, they are at the heart of the sensor actually technology, and they are actually very as I think Yoon presented today, I think they are very related to because they are, the semiconductor can actually help us to come up with the sensors. And here also you can see that the robotic vision market is also increasing. And this one is like an example of the asset tracking robot that's been used for the data centers, and they are using the semiconductor as well. Thank you for your time.
Thank you so much, Dr. Elahi. Now I would like to welcome all of our, welcome all of our speakers. We're going to have a panel now. We'll bring the tables front and center, and we'll invite all of our presenters to address any questions that the audience may have. So here we are at our Q&A panel. Oh, thank you, team effort. Please have a seat.
Enough chairs for all this people.
I want to thank all of you for such really interesting presentations. Is there a little bit of feedback? Oh, wonder where that's.
All the mics are on.
I know. I think all the mics are on. Maybe we can turn off the one in the middle. All right. I'd like to open up the questions to the audience. All right.
Of course. Thank you so much for presenting. One thing that I think this is sort of for the whole group, because one of the things we're talking about consistently over the last decade, right, is the increased reliance on semiconductors. Baheen had these pictures of what's coming for the global need, the global usage of semiconductors. And I'm curious, from all your perspectives, right, you're all researching this from different areas, but I know we have a talent shortage here. I know we have a manufacturing shortage. We also have a material shortage. So I'm just curious, as scientists, do you see a path forward where we don't come to some sort of cliff? We engineer our ways out of the need for materials and that kind of stuff, I guess. I know it's a broad question, but I'm curious.
I have a lot to say about that. Sure. But you want to you want us to have us like go down the line, or if it's for everyone? No. So I think that's a fascinating point, and it's like specifically like semiconductors are so interesting to me because it's like they're new, they're growing, they're super important now, but they've been important for so long, like ever since they were really discovered. They're kind of these amazing materials. And then you hear like people talk about like these brick walls that we're possibly going to run into as we get smaller and smaller and smaller. At some point, there are limits. I see a lot of possibilities. I think particularly as you go to these lower and lower and lower dimensions. I didn't talk about, well, maybe even with the color centers in diamond, basically. Like, so there's a defect. Many of them are known. Some of them are not known. There's actually the slide that I showed, like I sort of highlighted a few things, and that was I think it was a geology like resource online that you find, and it was fairly new. But if you just look through the descriptions, here's like a bunch of different resonances. This turns the diamond pink. This one turns it yellow. This one turns it blue. This one turns it something else. And for like 20% of them, you look at the little description and it's like origin unknown. And partly that's just because you can just put different elements in. And when you're really, really small, you can, you put 2 or 3 next to each other. That's like that. The permutations just increase. And so I think there's tons of things that we haven't tried. Lots of possibilities for just exploring these. And maybe one of the problems is actually not like there's so many materials out there, is like knowing which ones to even try for. And so maybe we need like some combination of like actually physically trying things in the lab, but then also having good guesses as to like, what do we think is going to make a good bet? And then maybe that's exciting to see sort of like all these machine learning and these sort of artificial intelligence ways of like quickly going through databases of possibilities just to identify even candidates is maybe an equal problem. I think there's almost too many materials as opposed to too few. But that's I guess my personal perspective. I'd be curious to hear if other people have different thoughts on that.
I have no experience in material, so I have nothing to add to this.
Maybe I can talk a little bit on this because we use a lot of materials in biosensors, and what our strategy from engineering side is we are trying to make them more reusable. For example, the sensors we developed, many of them we try to regenerate them, not just using them once. And we try to make them smaller and save some materials. And we're using nano-sized material to reduce the cost and reduce the use of those like non-reusable materials. So that is from an engineer perspective of view.
And I also think that, that can be a concern too. And this is what happened during the COVID time. When I remember that, we had like an area that they had like a nice bridges, but they needed the lightning for that. But because they didn't have like a chips, then they were not able to, kind of have like an opening for that bridge that was, affecting the traffic and, those type of things. Then I think that can be a concern. And also, like some people, for example, that predict that there will be, for example, someday that for the problem, for example, in water, there can be a war in water, or then I think that probably, if then that's important, that how much resources that we have here and how much we are importing from other countries. And also with the advent of the AI, quantum computing, and so on, if more and more materials need to be used, then I think that in some point probably, we need to strategize that and thinking that what will be, the usage from 5 years from now, 10 years from now, 20 years from now, and are those companies that we are importing the material here, they are still interested in to do so or not. And also at the same time, probably like for example, the fossil fuels or those type of things that we are hearing that, like I had, for example, literally yesterday, research from a student related to the offshore turbine that they are using, like getting energy from the waves from the ocean, and at the same time, having the turbine there. Then probably there will be some also other solution that we can think of, that we are, kind of less and less dependent to the specific type of material, a wide range of that, or, the type of that which is, for example, more useful. But at the same time, I think that makes sense. That can be like a concern here, and also with the huge, I think the growth of the AI, that even it's actually far away from all of us, and and even the policymaker, I think that there should be like a momentum there that what type of policy we need to have for the AI, and even I can see that at the educational level, then those are the concerns that should be also, more discussion on that how we need to take care of that and how we can equip ourselves and also students for the future. Thank you.
Thank you. Other questions from the audience? Great.
Can I get a question? Thank you for your presentations. And not necessarily everyone has to answer, but would you be offer sharing any of your advantageous collaborations beyond San Jose State and how you leverage that, right, to further your RSCA?
Right. Any synergistic collaboration.
I would just like to say another call to action pitch for joining NextFlex. Well, we already have joined, but to really get involved and to reach out to those resources that are available. Kind of in reference to Richard's question earlier, while I don't have a materials background, I think this is kind of where the importance of innovation comes in, and to bring in various different perspectives from not only those that address industry needs, but how we can really apply the academic research to make grounds on innovation. So I think it really will come down to being able to integrate multiple perspectives and bring a lot of different parties together.
So for collaboration, you know that I'm working with LAM research, and actually I wanted to present my research with LAM today, but we signed an NDA, so we cannot say something about it. But here is the thing. So we have many companies around here that are very interested in this kind of stuff. How to motivate them to come here and invest, I'm not sure about that. I took advantage of the like a relationship between LAM research and us, presented something to them. I can't say the topic at least, but here is the thing. So when you have the production line and you want to train deep learning models, the biggest problem that we have is we don't have data set. And these images that you saw from those alignments, I used David Parent's lab to took those. And all the alignments that we took picture, we came up to 800 images, which is not a lot at all when you want to train a deep learning model. So our proposal was, instead of just using real images, how about we use synthetic images? So we generate synthetic images, but there are some issues with with the models that are trained on synthetic images. So we came up with a solution that how to solve those problems. And basically we are studying or providing LAM research with a guideline that how to generate synthetic image with any application that you have in your company. And based on those images, train a model, just run the model, and it's going to work not as good as the models trained on real image, but close enough. So yeah, I mean, about the collaboration, I believe that we need to encourage more and more companies like LAM to come here and invest. So gives somebody like myself an opportunity that I hired 4 students on that project. So one of them graduated, took a job at Amazon. The other one graduated and he's working somewhere as a quality engineer, and 2 more working this year also. So again, these kind of money and collaboration provide us with, the platform to work on that. But I'm not expert on how to reach out to them. Probably Jason can, help us with that. I believe that that's the solution, at least, to get in touch with companies.
I have 1 or 2 comments. So I love that question, actually. Collaborations are, I think, one of my favorite parts, actually, of doing research and being a professor is, like, every time I meet somebody new, there's, like, I get all these ideas, and there's, like, all these possibilities start to open up. And I think, so your question was kind of about the past. I think from a practical matter, my research specialty is spectroscopy, which is basically taking lasers, shooting them at things, looking at what comes off. It's hard. In and of itself, that field is a hard field. And so in order for that to be successful at San Jose State, but also everywhere that I've been along the way, I've kind of done different versions of spectroscopy all along the way. We look at the samples, we take the spectra, we work on the optics, we work on the analysis system, but we don't actually make the samples. And so actually everybody I think sort of relies on those kinds of external collaborations And so collaborations with, even when I was at the University of Michigan, like a lot of those collaborators at Sandia National Laboratories, collaborators at MIT who actually made and procured the sample for us were absolutely critical in being able to do any of that research. So that I think is really important in terms of helping out San Jose State. I think it's also kind of fun to think about ways that San Jose State can help other institutions at the same time. It goes both ways. And I think one of the things that I realized, I had the opportunity to visit Air Force Research Laboratory in Dayton, Ohio, a couple month or two ago or something like that. And one of the things I got to see while I was there is that they have incredible facilities. There's just like lots of rooms and lots of equipment. And for whatever reason, they don't have a ton of people or students. And we have a ton of students, and our facilities are sometimes not where we want them to be. And so I think it's really fun to sort of like imagine, are there ways in which sort of we can provide things to places like national laboratories, or and then they can provide things to us. I think everybody wins in that scenario.
Yes, I agree with Chris. I really love collaboration because it opens up some new opportunities. So in my case, I have some collaboration with government agencies and also national lab and other universities. My research is more depends on like what they need. But some cases is they don't know what I can offer. So it's important to have the opportunity to be able to tell them what our capabilities are. Like I talk to some people like they ask me, what's a biosensor? I tell them, okay, glucose meter, do you know that? That's a biosensor. So they don't know what we can do. So once I explain to them, they're like, oh, okay, that's interesting. I think we have potential to collaborate. I think that kind of opportunity will be very important for building any collaboration effectively. Thank you.
And I also think that probably at the university level, we need to be more strategized on that. For example, I was just talking with Jason and Barbara that we were just, kind of discussing that probably, we need to kind of forming like a interdisciplinary group of the faculty with actually their clarifying their expertise, and then trying to actually target the different type of industry related to semiconductor or even other industries to actually show our knock the door and actually trying to actually show off what we are, and then trying to actually focus on like a mutual trust, and also at the same time the value sharing or what will be the motives or driving forces for them to actually trying to collaborate with us, then how we can come up with like a win-win, kind of platform here that also it will be motivating for them. Then, for example, if we are equipping and upskilling the workforce here, then how they can, for example, benefit from that, or any type of, for example, any successful model or any benchmarking that can be, for example, used here to help us to leverage the collaboration with the external, kind of industry, if we are focusing on that.
Great, thank you. All right, well, we are a little bit past noon, so I want to thank all of our presenters for a very interesting and enjoyable hour where we learned lots of different things about semiconductors, the CHIPS and Science Act, and how SJSU is addressing those concerns. Could I get the room to provide a round of applause, please? Thank you so much. I want to thank everyone who's on the live stream for your participation. So this concludes the formal part of our hour, but we have another hour for the room. And so I invite everyone to grab a bite to eat and to continue to talk about all of the great things you've learned today. Thank you.
Thank you.